Thanks for coming to sunny California. For those of you that have traveled from far to come here, I know some of you have come from halfway around the world. Beautiful day. This is just fringe benefits of having the conference over here. Want to introduce the first tutorial session. We thought we'd put together an overview of various design, chip design or design approaches, looking at ASIC design trends, NRE costs going up. What are the choices these days? How long does it actually take to design a chip? On one end, you said ASICs, NRE costs. The other extreme, programmable guys say, use a CPU. You can write a program. And then, well, how much performance do you really get out of that? In between are probably somewhere the FPGAs. FPGAs, time to market used to be a selling benefit. I think that's gone as well. So where are we really at? So we thought we'd bring up some experts. And we've sort of assembled a nice session with the three gentlemen standing over here. Maybe you can raise your hands. ShepardSiegel, he's here from Mercury Computers. He's going to tell us about the struggles that Mercury is going through in terms of picking so Mercury is not a chip company. Mercury is a consumer of chips. And so they struggle with what is the right architecture for our design needs. And so Shep's actually in the office of the CTO over at Mercury. And he's been tasked with assessing different chip technologies and which might work best for Mercury. So he's going to have a nice insightful talk. We also have here David Witt, maybe a quick wave of hand. So David's here from TI. He actually heads up the design team responsible for all the digital components in all the wireless chips at TI. So he's going to give us a nice presentation in terms of the struggles that they're going through, the cost drivers, their pressures, and certainly try to catch him after the presentation as well for some ongoing questions. And then we have here finally Peter Alfke. He's here representing the programmable logic camp. Peter's been around. I would say Peter's probably been working even before I was born. So he certainly has experience in many different fields. A little bit of trivia. Did you know that one of the gentlemen actually is a winner of an Emmy Award? Maybe we'll keep that a secret until after the presentation. The other two gentlemen actually worked at AMD together, maybe knowing it or maybe not knowing it. So anyhow, with that said, I'd like to introduce ShepardSiegel, who's going to give us an overview of processor choices that Mercury goes through. And say, welcome, Shep, and enjoy the presentation.
Thank you, Ralph. Good morning. Wow, what a dive. This is great. So I'm ShepardSiegel from Mercury Computer, and today I'm going to take you through a tour of the work and my life, I guess, up to this point. And hopefully this will be insightful, and that you who've taken the time to get up this early Sunday morning, a gorgeous day outside, and you're here in this dark room, will find that it was worth your while to go through this. I want to make the presentation as interactive as possible, but I also think since there are so many slides that it may be best to queue up the questions towards the end. However, if there's some particular point through the course of going through that you feel passionate about and someone in the audience wants to press the pause button, please do so. I think that will engage everyone as well. So let me just jump right in. What am I talking about today? Well, as Ralph said, David's going to talk about the DSP perspective. Peter's going to talk about the FPGA perspective. Mercury's kind of been, for me, the 5 years that I've been there, this primordial soup of processor heterogeneity, and hopefully these slides will provide some insight to the challenges that myself and Mercury have go through in selecting a particular processor, and you could synthesize that into your own concerns over why a cell over a GPU over an FPGA. So I wanted to start essentially by communicating the topic, what a great frickin' time it is to be an engineer, right? We have all of this, we have this embarrassment of technical wealth and capability, but perhaps there's even too much choice, because frequently it isn't about doing something great for the companies that we work for. It's about time to solution and time to money. And that's a bit of a problem, or it can be. And maybe we'll talk a bit about where we go with that. So essentially today, there are these three thoughts that I want to bring forward. There's this heterogeneous composition aspect to the talk, which is that if we're real clean about our interfaces, we're going to be able to stick processor architecture A with processor architecture B by virtue of the fact that we compose the system well. That composition requires some constraints, and we'll talk about that. And I'm biased because my responsibility in Mercury's organization is towards reconfigurable computing, but I think FPGAs are truly unique in this processor trade because of their reconfigurability. So the problem space that we have before us, you know, the throughput, latency, cost, space, weight, and power, which in the defense segment they simply say is SWAP. So if I say SWAP, it's space, weight, and power. Everyone here is familiar with that. Well, I believe everyone here is familiar with that. Historically, sort of how long it takes to get the job done, how much it's going to cost, how much can I reuse this bit of IP, has been a second-order concern. And from my vantage point, this has changed quite a bit in the past couple of years. Time to solution, time to money, just is marching to the top of the stack as one of the most important issues before us. So the concepts that we'll go into here are applicable to a specific single system on chip IC like there might be in a handset, but the scope of the type of products Mercury produces is generally much larger than that. It's not a single chip, it's a board which is a collection of chips, or a system that's a collection of boards. So while the concepts that I'm throwing out here and launching into the audience, hopefully no one's getting hurt, can apply to a single system on chip, I think they're more generally applicable to larger scaled systems as a whole. So let's dig into that. So processor heterogeneity, big sounding words. Well, what are we talking about? Well, we're talking about the selection at the chip level of different types of processors. So this isn't a complete list. It's certainly not a complete list of vendors, but simply wanted to ground the discussion space over, we're talking about GPPs, multi-core GPPs, GPUs that increasingly are executing code that look like the code that's running on a GPP. Cell, which is just well, I shouldn't say it's just. It is another instance of a coarse-grained heterogeneous processor with a PowerPC and a bunch of these nice SPEs. DSPs from TI and the like. Ambric, polymorphic computing architectures like the Monarch architecture, another coarse-grained heterogeneous architecture, and of course FPGAs. So maybe a bit in front, why FPGA, why not FPGA in all of this trade? You guys said earlier that it's FPGA stands aside from the others in some way. These bullets speak to that, sort of the right-grained, fine-grained circuit composition, the combination of intimately bringing your I/O next to your logic, and application-specific memory hierarchy, the ability for a circuit designer or a system designer to get the right blend of memory to processor on the chip itself, even without venturing off the chip to the fabric or interactions with other chips. And lastly, in this list of bullets for why FPGA, what I like to call the final frontier for reconfigurable computing, which is the time multiplexing of the FPGA fabric. Now, unlike an ASIC or any other hard ASSP, this ability to essentially go, I don't want this ISA anymore, I want this new one, or possibly doing that dynamically while part of the FPGA is running, it's the future. It's been the perpetual tease in the FPGA space for almost a decade now, but we do see some advances there. Well, why not FPGA? Sort of big in the reason why FPGAs might not make it into a particular application is that to get that order or order and a half of magnitude of gain up on another processor technology that's necessary to amortize the added design pain that RTL designers have historically gone through, you would typically be doing 2D spatial programming of your algorithm. In other words, there might be some functional representation of what you're trying to accomplish on this processor, but at the end of the day, you're composing this 2D array of switch boxes, lookup tables, and flip-flops to realize your application. And that's not going to go very well when Altera or Xilinx change the substrate or the organization of the switch box, and a lot of that hard effort washes away. And lastly, why not? Well, because of that very aforementioned need for spatial design to get the most out of the fabric, there's frequently this coupling of the domain application engineer and all of her knowledge, for example, and the RTL circuit designer and all of his knowledge. And they're seldom the same person, and that coupling of roles isn't good for most companies where there's finite design resources. So how do engineers conquer these problems? Well, I don't know. I often cut them into little bits and pieces because I can reason about smaller, the finite volume of my brain says I can reason about a small problem better than I can reason about this big problem with lots of coupled concerns. Divide and conquer is a good thing if you can divide and conquer and have some methodology that enables those little pieces that you've divided into to be composed back together again. Hallelujah, that's a great thing. So we talk about separation of concerns all the time, and I put down a couple of bullets just because through the rest of the talk I'll meander through these various roles, but I thought I would gather them together here. The separation of communication and computation, that's age-old, right? Systems that are driven on throughput pretty much want to separate or orthogonalize their compute from their communication, if for no other reason than to overlap them and to form this real coarse-grained, task-level, sequential bucket brigade that's going to have very high throughput and isn't necessarily doesn't hit a critical path if a compute or a communication link slows down because you can provision one without provisioning the other. Separation of application from architecture was what I talked to in the previous slide about bringing the person, making some platform or some dividing line between the domain application expert and the person who knows all about RTL circuits. The architecture and implementation is yet another fine platform between the architecture and that actual implementation. And lastly, the specifier and implementer, which we'll get to shortly. I like to use the term velvet handcuffs when talking about making constraints on choice in design. Essentially rules that design teams or designers or the parties delivering components to be in some final assembly will follow. Those rules are sometimes necessary to build an environment where components can be composed in a reasonable fashion, where adding one component, for example, doesn't change the behavior of another, or that the effort of adding a component is proportional to itself, not to other components that might pre-exist in the system. With these velvet handcuffs, and specifically when I use this term applied to interfaces, we typically talk about producers and consumers, masters and slaves, initiators and targets. And the most obvious connection between these matching tuples are when they're like to like. If this shape is identical or fits the other shape perfectly, this like-to-like interaction should certainly work. It should certainly interoperate. There'd probably be very lightweight cost of binding the two together. But the cost of coupling two interfaces together as they become dissimilar can grow. We've all seen many times where where an interface problem was connect this producer to this consumer. They're about the same, but there's a change in clock rate, or there's a change in bus width, or there's a change in flow control. And it kind of becomes a gray area to the point where all of a sudden you're saying you have some producer and some consumer which can't really, in the engineer's mind, conform to each other. So the notion of velvet handcuffs, I think, is a value, certainly in like-to-like, like-to-similar, but as you move to entirely dissimilar protocols, it begins to fall apart. One way an internal taxonomy for describing these interface patterns, or velvet handcuffs, are to bin them into templates for common interactions that IPs might have. And I use IP in a broad sense here. It could be a circuit in an FPGA. It could be a subroutine inside a cell SPE. It's some expression of logic that will be realized mapped onto some architecture at some point. And these IPs that do work, so I'll call them workers or IPs, typically have command and control. You might configure them with certain parameters before you tell them to go and do their work. There's typically in a streaming data plane, some sort of producer or consumer. Sensors are obvious examples of that. There's frequently some type of messaging data plane. So this is when you have a one-to-many or many-to-one. It doesn't need to be, I mean, it could be one-to-one, but frequently some distributive or collective operation between processes where you're sending data as messages as opposed to block sequential streams. And lastly, we've worked out a separate pattern for memory access because separate from shared memory of a larger program, most IPs, whether they're software programs or IPs that are doing some job, need some type of local high-efficient memory access above and beyond how they communicate in the larger system. So there's a lot of work in both the software and computer-aided design communities about that. One of them is intention-revealing interfaces. I point out that there's a lot to draw on here, and my own experience has been to borrow from work that others have done and incorporate it into my own rather than be the pioneers with arrows in our back trying to come up with yet another paradigm for representing interfaces. I like this slide that talks about complexity because a lot of this, well, my talk in general is about trying to wrestle that complexity. And when I hung this slide up in my cube, some of my colleagues came around and they have a funny look on their face, and it's about, many of them mistakenly think, oh, so you want to build simple systems. And actually, no, I want to build complex systems that solve our customers' problems, but I'd like to spend the least amount of money to do that, and I'd like the engineering programs that do that to go as easy as possible. So this slide makes me feel comfortable that we can wrestle complexity, we can address a complex interaction as long as we're mindful of the fact that there's cost in that great heterogeneity, that all these extra choices, optimizing to have the best process here or the best communication in a particular scenario, isn't always the best thing. If I can regularize the pattern, that'd be simpler, that may cost less. So a quick slide that just sort of scans through. Earlier in this presentation, I ranted on about system on chip and how Mercury does things that our end product typically isn't a particular ASIC that's in a handset. It's actually a collection of chips on a board in the system and the same pattern repeated higher up through this hierarchy. I think it is important, though, to understand that some of these concepts can be applicable across the board or only specifically applicable at one level or one scale of this integration. More or less from high to low, these bullets enumerate those various levels down to what I call the individual IP worker, or and again, I have this FPGA mindset now where at the end of the day, you're going through all of these gymnastics to provide a worker with an environment to get its work done. So some of the goals that we have in abstraction is trying to decouple decoupled influences on different parts of the system. We'd like workers to just work, get their job done, and infrastructure surrounding that worker to cope. An example of a worker might be something that solves a linear system or does multiply accumulates. The infrastructure around that worker would be the environment necessary to support it. If that linear solver required a buffer, a local buffer of memory, it would be the provider of that local memory. So that's the distinction I make here between workers and infrastructure. And I think it's a key point that engineers generally want the path cleared to get their job done. I'd like it, it would be a great job for me if the tough part around was done and I could just get on with my work. But I guess I'm actually in a business where I'm doing that for other people, so maybe it's not such a bad thing. But there is value, I assert, in clearing a path so that the designer's mind is in his or her own problem space and not that in what the infrastructure provider is providing. The other goal in abstraction is to facilitate interchanging components. I might want to share a component with my customer, my vendor, my competitor even in an open community. And all of this is necessary because the silicon is evolving almost continuously. The application domains are evolving almost continuously. And verification challenge, which is attempting essentially to reduce costs of manufacturing and other fixed costs around building these systems, are essentially all moving forward continuously. I mean, we can talk about process node quantization and how these are 18-month big hits. But the reality, just in the FPGA space alone, is if you look at Altera and Xilinx's chips as they've come to market, it's been nearly a continuous launch of product. And if you were to peg, for example, all of your eggs in a certain basket on a certain microarchitecture based on certain switch boxes, you'd be doomed. Or at least you'd be spending a lot of money that you wouldn't necessarily need to spend to accomplish the same goal. So here's a diagram just of a what does this look like? It looks like a modem of some sort that's receiving data from an A to D on the side, passing data through two FPGA compute nodes, farming it off to a general purpose processor, and spitting some data out gigabit Ethernet. There's another node that's on that control fabric network that's perhaps choreographing the other GPP and FPGA actions. So at a sort of vague application level, this slide speaks to the type of segmentation that one might expect between compute and communication. The gray-greeny lines between the boxes here happen in this case to be heterogeneous communication. There fortunately isn't quite as much choice in communication as there is in computation, so that choice is a little easier. But again, this slide, the intent here is to say we have these compute nodes. The nodes might contain multiple workers, IPs, functions, subroutines that are actually doing the work. And this is the heterogeneity that we're talking to. So in this slide, it amplifies the point I made earlier that that what we're trying to achieve, what Mercury is trying to achieve for its customers, what I think many engineers are trying to achieve to add value in their work, is that the application gets to specify, the customer is always right, and say, this is my fundamental challenge. I need this throughput, this cost, this latency. And the architecture then has to cope. It's the problem of the engineer to say, is a cell right for this? Is a GPU right for this? If I use FPGAs, is this design methodology right for this? And I think it's okay to have this asymmetry. It's taken me a while to get to this point, but this slide clearly asserts certainly my own personal bias that it's worthwhile to have this asymmetric bias in favor of the application over the architecture because if for no other reason it's closer to the money or it's closer to a particular solution. So this is kind of the cool segue in my talk. Ralph, our session chair, when I was putting this together, thought it would be helpful for me to draw on some of my own insights. I kind of felt a little awkward in doing this, so we're going to take a little shift in my presentation to a bit of my life story and how I got to have this opinion about processor heterogeneity, and maybe I'll be able to pull it all back together. So. The next couple of slides, I'll go through sort of the three companies that I worked with after school. Basically, at university, they teach you that math and science is engineering. Great, you get all the bits and pieces. I'll talk a little bit about my experience at Ampex with a digital video special effects box called ADO, where a lot of money and fame came real quickly. Well, the money didn't come to me, but the fame did, I guess, or not. How that segued for me into a startup that ultimately failed at Datacube, and how that ultimately brought me to Mercury. So, flashback to early 80s in the Bay Area here, just up the street in Redwood City. About a dozen engineers, of which I was one, went to work on a digital video special effects box at a company with the gods of analog design. I mean, this is the Ampex, invented audio tape recording, invented FM recording on tape. I mean, so we were basically the grad school dropouts that had gathered together to try to exploit the nascent digital signal processing in broadcast market. There was the dawn of flash converters, the dawn of TRW multipliers. And essentially, we put together this concept for a product that would be this extremely high fidelity 2D DVE. It takes a television image that's 2D and moves it around in 3 space. I was really fortunate to hook up with a mathematician, Steve Gabriel, who essentially invented ADO in the sense that he realized the separability of perspective, and that through that separability, he was able to convert an n-squared cost problem into 2 significantly simpler 1D problems concatenated together. And that realization essentially was the product roadmap for ADO. It's a terrific story. I'm not going to tell the whole story here, or at least I'll try not to. But it for me, made it really clear. I said at the beginning of this talk, what a great time to be an engineer. Back then, it felt like it was a great time to be an engineer, because all of a sudden, digital signal processing for live television was realizable. I won't go into all the details. I actually think the Ampex Museum was taken up by the Stanford Museum here, so if you're curious, you probably could kick around and find it, maybe not. ADO the ADO signal system was impressive for its time. It was 27 boards. It was about 200 amps at 5 volts. Essentially, it was a 13.5 megahertz signal system. We used small synchronous proms to do all the little lookup tables. Earlier when I was talking about FPGAs and having to make this 2D spatial design, back then everything was 374s, 2-to-1 muxes, full adders, and you very statically schedule that machine by drawing it out on paper with templates. From my own perspective, the real takeaway from Ampex, or one of them, was the beginning of programmable logic. Berkner had just invented the PAL and MMI. I remember distinctly getting all of this flack by putting the first PAL in an Ampex product and making sort of the accidental discovery, I can send this board out for design, for the board out for PCB design before I actually know what the logic is going to be. And I know that seems commonplace now, but in 1982, that was unusual. So there are a bunch of us. I think I'm on the lower left there, see, with hair and everything. But it was The product was terrifically successful. It made $500 million for Ampex. The design team got an Emmy Award. You have a naked gold lady and everything. We had the type of fame that 20-something engineers would have at the time. All of the broadcast post-production houses were clamoring for this machine. So whether it was beer commercials or Saturday Night Live openers, we had that visibility. So what did everyone do at Ampex? Everyone left because they wanted to play that out elsewhere. Gabriel went off to Microsoft and was instrumental in a lot of their graphics directions. Phil Bennett, who was the hardware lead, went off to found Abacus, which is where the original video disc recorder for television using hard disk technology was developed. And I went to this little startup in Massachusetts called Datacube. So Datacube at the time had just been doing frame grabbers and wanted to break into image processing, and Stanley recruited me after seeing ADO saying, oh, I'll make you a millionaire in, I think it was, I'll make you a millionaire in a year and double my salary. Well, he did the latter, but it was a good ride. Stan passed away last year, and he was a big influence on myself and many others in a very positive way towards the bit I touched on earlier about biasing things towards the application or talking to the customers. Perhaps more than anyone else, Stan made it really clear that as engineers, we really should be doing things that add value, not because they're technically feasible. And I see evidence of this all over the place when any vendor comes out with any new feature. People seem to clamor to use that feature just for the sake of that feature, not necessarily because it's going to bring any value to the marketplace. And I really think Stan was head and shoulders above the rest of being keen to that. That while you could certainly have fun, it's not all about making money. At the end of the day, it's about bringing value to your customers. So Datacube was fantastic because Stan's background from AMD MMI allowed Datacube to be a petri dish for programmable logic. When I came there, the company was already using PALs, but it was immediately obvious that Datacube was going to be driven heavily by ASICs and FPGAs at the time. The company hit its zenith in the late 1980s or early 90s, doing these 6U integer image processors. The joke about my work at the time, because we're always trying to turn Fmax up by bisecting the critical path, was that SHEP stood for should have everything pipelined. The VP of engineering at Datacube came up with that. And interestingly, this is artwork that shows sort of an airbrush photo of one of the early convolver boards that Datacube had done. The blue cables on the front, as an interesting aside, entirely independent of this talk, are playing out a pattern that's repeating today in optical networking, in that the combined bandwidth out the back and out the front wasn't adequate at the time for the board. So Datacube's solution to that problem was actually to have these point-to-point cables, which were synchronous links between different boards in the system. I find that interesting because at the time, one of the critiques levied against Datacube against a competitor like, say, I don't know, Mercury, was that we didn't have a switched fabric. We actually had this statically connected fabric. And now, because of the need for higher and higher bisection bandwidths in the system today, that's playing out again optically. Anyhow, by the end of the 90s, FPGAs were driving all of these integer image processors that Datacube was making. Here's an example of one of them. They're being used in digital angiography, web inspection, machine vision. That's probably a Xilinx 2000 or so device, and a QuickLogic DMA engine serving as both a PAL-like device and the DMA agent between PCI and the processor. So all of the dedicated hardware, the TRW multipliers, the fancy YTech floating point chips, all gone in favor, basically driven out by FPGAs. But there was a problem. Datacube was making the specialized MaxVideo hardware, which was excellent. It had the specialized object-oriented image flow software, which too is excellent. This is the classic Christensen disruptive technology in the sense that the PC, the Intel processors, x86 processors of the day were getting good enough for almost every application and every market that Datacube was in. Datacube had point hardware and point software in niche markets. That's not a good thing. And like the time often given on the end of an airplane flight gone bad, essentially the company augured into the ground right around 2001. So I was real fortunate. I ended up at Mercury, a place where I still am now. And I've always regarded Mercury, even before I worked here, sort of the gods of heterogeneity. Mercury has been doing multi-computers, distributed memory multi-computers, forever. Way back at the dawn of time, they were taking bit-slice 29/116s and connecting them through some type of communications network. And the company, I believe, has grown based on their embracing heterogeneity from day one. As time marched on, the bit slice was replaced with other processors, some DSPs, but to the point today where GPU cell, FPGA, polymorphic computing architectures like Monarch are connected together over over various communications channels. Before I joined Mercury, the company did have the wherewithal that FPGAs, in the late 90s, FPGAs were going to become a dominant force in the industry, and had put a business plan together, essentially saying, let's staff and put together a group to do reconfigurable computing, to make FPGAs into first-class processors sitting alongside, let's say, a PowerPC, an x86 processor, a GPU, or a cell. So that was good, because when Datacube augured into the ground, it didn't take too long to get hired somewhere. So I'm going to tell a little story about the first program I worked on at Mercury, and that will serve as a segue back into the talk that I so cleverly veered off of a few moments ago. So the Backprojector is our 3D reconstruction is used in medical imaging to take the multiple scans made by a CT machine, for example, and make projections along any axis so you can render the image. I'll show pictures in a moment. FPGAs are one really easy way to speed that up. We saw an opportunity to get a 10 to 20x speed up over even Mercury's tuned accelerated GPP solution. So the operation is essentially it's a vector matrix mold. For the FPGA, there are many aspects to the entire rendering pipeline, but the heavy lifting, the inner loop that really needed acceleration for back projection was the vector matrix multiply inside the inner loop. And again, suspiciously, so many things in most people's careers seem to repeat over and over. Mine seems to be sort of this finite difference, repeated some accumulate pattern that was present in ADO, that was used in the warping products at Datacube, and again played out in the Backprojector at Mercury. So another diagram essentially detailing some of the quantities around how the input data was sliced up to be reconstructed to actually have a volume that some back-end tool ultimately rendered to the screen. Interesting about this, again, why did this work so well with FPGAs? It was a precision significantly less than what you would use single precision float for. So while previous solutions might have done all of the single precision floating point, it was found that we could get within an LSB or two by using the 18-bit multipliers that in that time frame had just started to appear inside contemporary FPGA architectures. So this board was one of the first, this PCI, the extended length PCI board was one of the first FPGA boards that Mercury had done. Before then, Mercury had